Hello, everyone. My name is Junqing. I'm a PhD student at Yale. Welcome to my AlChE virtual talk. My topic here today is polyoxymethylene ether as potential dual fuels with low sooting tendencies. So polyoxymethylene ethers, or POMEs, are this group of compounds with alternating carbon-oxygen structures. They could be derived from biomass-derived methanol, and then through further dehydrogenation, we could get what I call methyl POME here, which are ended with the methyl groups. So methyl POMEs have been discussed a lot in the literature because of their low soot emission and high sitting numbers. But it also suffer from low energy density and high water solubility. So to improve this to improve these fuel properties, what we proposed is to do end group exchange. So with bio-derived larger alcohols, we can replace the methyl groups with larger alkyl groups, what I call alkyl POME here. So with actual carbon, we could have higher energy density and lower water solubility. Also because of the carbon, the soot emission will be presumably higher. It will be interesting to see how the soot tendency of the alkyl POMEs compared to the methyl POMEs. So why should we care about soot emission? The soot emitted from combustion is the second largest source of climate change, also known as black carbon. So here is a TEM image of the soot particles from the flame. We can see that the diameter is around 20 to 30 nanometers. So because of it's small, it could enter our cells. So the atmospheric particles, which include the emitted soot, cost 4.6 million annual global deaths. So soot itself has a short atmospheric lifetime. Therefore, if we have emission reduction of the soot, it will have an immediate effect on environment and human health. Soot is particularly interesting when it comes to biofuels. So because of the presence of the oxygen atoms, the biofuels usually have a lower sooting tendency compared to their petroleum counterparts. So the different fuels actually have different tendencies to form soot. Here I have two pool fires, ethanol on the left, and benzene on the right. So the bottom part of the flame, which is blue, is coming from the chemiluminescence of the activated intermediates such as CH star. The tip of the flame where it emits orange light coming from the black body radiation of the soot particles. So here we can say that the benzene emits much more orange light compared to ethanol, even saturate part of the camera. Therefore, the benzene have a higher sooting tendency than ethanol. To explain that, we can take a look at the decomposition pathway. The ethanol will decompose to some small hydrocarbons, and then they combine together to form benzene, then continue to form PAH, and then to form soot in the end. Therefore, we can see that the benzene is at a downstream of soot formation compared to ethanol. So that's why benzene have a higher sooting tendencies than ethanol. So to quantify the sooting tendencies of POMEs, here is the flame we are using. Air as oxidizer and fuel and methane, nitrogen, and dopant. And the dopant we're interested at the fuel mixture. So we have our laminar cold flow flame here. So sequentially, we dope 3,000 ppm of a test compound that we're interested, water and heptene in the fuel. Then we'll measure the maximum soot concentration of each flame with line of sight spectral radius, or LSSR. So that is this black body light emission from the soot. And then we're rescaling the LSSR into yield sooting index, or YSI, as using this equation. So the YSI itself is a mole-based intrinsic field properties, which is independent of experimental conditions and specific apparatus. YSI is defined in a way that benzene have a YSI of 100 and YSI of a field that produce no soot is around 0. So to simplify the structure of the POMEs in this study, I named the POME as R1 and R2, where N is the number of oxymethylene group in the middle. R1 and R2 are the N terminated group, where M stands for methyl and B stands for N-butyl, etc. So for example, the dimethoxymethane here will be called M1M, and the dimethoxymethane here will be called B1B. So the group exchange I mentioned at the beginning, if we do butyl exchange using N-butanol, the M1M will change into B1B. If we do chain propagation, where the number of N increase and the POME grows bigger, then we'll begin with M1M, then get M3M, and then M5M when N gets bigger and bigger. So with that, let's take a look of some of the YSI result of POMEs. So here, the blue bars are for the POMEs. The black bar is a certification diesel called CF diesel. The orange bars are diesel bioblend stocks, which are also biofuels proposed by Fioroni et al. So we can see that the diesel have the highest YSI, then the bioblend stocks, then the POME have the lowest YSI. For the for the alcohol exchange, so after alcohol exchange, the YSI increase from MNM to PNP to BNB, but they are still lower than the certification diesel and the diesel bioblend stocks. Here I'm plotting N, again, the number of oxymethylene group versus YSI. I showed the structure of the POMEs in the plot also. Here are some observations. So first, the YSI decrease as an increase. And second, the YSI of M4M and M5M are negative, which means that they are lower than water, even though they are oxygenated hydrocarbons. The YSI also increase when carbon number on the side chain increase. So from MNM to PNP to BNB. So here, to explain this interesting observation, there are several hypotheses. So first, it could be a thermal effect caused by the temperature change. It could also be a dilution or chemical effect caused by the decomposition products. So for the thermal effect, people usually use adiabatic flame temperature to quantify that. So it is the temperature of the fuel mixture you are interested in. Our case, methane, nitrogen, and the test compound mixed with the stoichiometric air after reaching the chemical equilibrium under a constant pressure. So the plot on the right showing the difference in AFT of the POME fuel mixtures and the water fuel mixtures. So here we can see that the M&M have a higher AFT compared to the water mix. So a higher temperature will lead to a higher soot concentration because soot formation is a kinetic driven process. Therefore, we can see that the thermal effect didn't follow the trend I mentioned earlier. So the thermal effect is not dominant. We can't use that to explain our trend. And when it comes to dilution and the chemical effect, let's take a look at the decomposition pathways of the POMEs. I will not go into details just to show the global equation. So the POMEs will decompose up to N+1 mole of, so the M&M will decompose and produce up to N+1 mole of formaldehyde, then with a methyl group and a H radical. So because of the large the large mole of formaldehyde, it will lead to a noticeable amount of dilution from a dilution effect perspective. For the chemical effect, the methyl leads to some soot by forming some small hydrocarbons, but formaldehyde could hardly form any hydrocarbons because the carbon-oxygen double bond is hard to be breaked. And the formaldehyde usually dissociates to CO instead. So for comparison, other hydrocarbons such as N-alkyne could also have a large dilution effect via decomposition, as I'm showing here as one possible decomposition pathway. The alkanes will decompose to a lot of small hydrocarbons such as ethylene. On the other hand, the chemical effect of these small hydrocarbons will dominate versus the dilution effect. So that's why the N-alkyne have a much higher YSI than the M&Ms. So to wrap it up, the dilution effect probably dominates the POMEs. But in other cases, such as N-alkynes, usually the chemical effect dominates the YSI. So with that, to explain some of the previous observation of the plot on the right, so the YSI decrease as N increase, because as N gets bigger, you will form more and more formaldehyde, which leads to dilution. The YSI of M and M5M are negative, so lower than water, because the dilution effect of the decomposed formaldehyde is higher than the chemical effect of the methyl radicals. Third, the YSI increase as N gets bigger from MNM, PNP to BNB, because when you have more carbon on the side chain, you will end it with more carbon in the total hydrocarbons, which is dominated by the chemical effect. So with that, here are some conclusions from our study. The YSI of the POME decreases as the number of oxymethylene groups increases, probably because the dilution effect dominates over the chemical and thermal effect. The YSI of the POME are much lower than that of the certification diesel and most of the diesel biofuels. So after alcohol exchange, the YSI increases, but the values are still lower than the certification diesel and other diesel biofuels. So that's the end of my talk. I would like to thank DOE and the co-optimization project for funding this project I just presented. I would like to thank my group for their support on my project and on all other things. Some special thanks to Amma and Camille, who are undergrads in our group that contributes to the YSI measurement of POME. I would also like to thank Professor Yuan Xuan at Penn State for ideas on simulations and decomposition pathways, and Professor Nicole Levy at UC Boulder for her input in the decomposition pathway of POMEs. So with that, I would like to stop and take any questions that you may have. Thank you.